Hello guys, welcome to S Academicus. Today in this lecture I'll be explaining a design problem on dog leg RCC staircase as per IS 456 2000 and SP 16. So let's take the problem. So the problem is where we have to design a dog leg staircase for a residential building have hall measuring 2.2 meter and 4.4 meter. The plan dimension of the hall is 2.2 by 4.7. The width of the landing is 1 meter. The distance between floor to floor height is 3.3 meters. The riser and thread may be taken as 150 mm is your riser and 270 mm is the thread. The weight of floor finish is the floor finish considered as 1 kilonewton per meter square. Material used M20 grade concrete and Fe415 steel. We need to also sketch the details. Here flight and the landing slab span is in the same direction, that is the flight span longitudinally. So first we need to just list down the input details. We have FCK 20 MPa, FI 415 MPa. Landing, we have landing width as 1 meter, that floor to floor height is 3.3 meter. The size of staircase hall 2.2 meter by 3.7 meter. So let us assume the thickness or thickness of the wall, or if there is a beam, so the thickness of wall, let's assume the thickness of wall that is supporting the staircase is 200 mm. So now once we are done with the input details, now we need to just proportion the staircase. So let's get into the next. As per the given data, if these the riser and thread thickness is not given, then we just need to assume it 150 mm and 270 mm. The height, floor to floor height is 3.3 meter, height of each flight. So in this single floor to floor height, we have two flight. Dog legged staircase has two flights, so h1, that is height of each flight, will be h divided by 2, which is 3.3 divided by 2, which is coming around 1.65 meters. So the number of rises will be in each flight will be h1 divided by the height of riser. So h1, that is 1650 divided by 150 is equals to 11. So the number of steps will be 11. Total number of rises minus 1, because one step is your landing, mid landing. So number of steps will be 11 minus 1 is equals to 10. Width of the horizontal is, we have 10 number of 10 number of flights, and the thread of each flight. So I'll show you what is flight. This is your flight. So this dimension is 270 mm. So 270 mm into 10, 1 2 3 4 5 6 7 8 9 10, so which is equals to 2.7 meters, 27,000 mm. Width of the hall is 4,700 mm. So thus so we have two landings, so each landing width is 1 meter. So let the width step be 1 meter. So the width of first step, then comes your flight, then your mid landing. The gap between two flights is 0.2 meter. So now let's get back to, now we have to decide the depth of the waist slab. So the formula for depth of waist slab is L upon D is equals to 26. This is basically this is based on the your slab depth. We have that L upon 26 mft for continuous slab, L upon 20 mft for simple supported slab, L upon 7 mft for cantilever slab. So based on those formula, this is assumed. So assuming we have a partial fixity, effective length is equals to 4700 plus 200 mm. This was the width of wall. So center of width of the wall will be 4.7 meter plus 0.2 meter, that is equals to 4.9 meter or 4900 mm. So D is equals to L effective divided by 26, which is coming around 188 mm. So we assuming clear cover, effective cover of 20 mm, normal exposure or mild exposure plus 10 by 2. 10 by 2 is your width of your dia of reinforcement use, so which is coming around 25 mm. So capital D, that is overall depth, is equals to effective depth plus this cover depth. So it is coming around 213. So let's provide 215 mm, this overall depth. So based on this overall depth, we need to just decide the effective depth. Effective depth coming is 190 mm. So this was your effective depth criteria. So now once we have effective depth, now we need to calculate the load, the self weight of the staircase. So tan theta, we just need to find these dimensions, so that it will be easily to this is nothing but to calculate the dead weight of the waste slab in plan. So based on the hypotenuse Pythagoras theorem, these values are calculated. HT, we have thread, we have a riser. So based on that, we find theta is equals to riser upon thread tan theta. Then hypotenuse, we based on these two values, this is worked out. So cos phi is equals to T by H. The value of cos phi is this. So the dead load of the waste slab is in plan is this. This is your overall depth. This is your 1 meter width, 1 meter width into area. This is 25 kilonewton per meter cube unit weight of your concrete cos phi. So which is coming around 6.14 kilonewton per meter square. Floor finish we have been given in the problem, that is 1 kilonewton per meter square. Weight of each steps rise by 2 into 1 by 1 into 24. This 25 is the 24 is without reinforcement. Imposed load, live load we have been given 3 kilonewton per meter square. So total W, total service load, this is service load is coming around 11.94 kilonewton per meter square. So ultimate load, that is design load, is multiplied by 1.5 into your service load, so which is coming around 17.91 kilonewton per meter square. So now the design of the second slide. So factored bending moment, first slide and second slide, there is a typical design. So the factored bending moment of second slide taking partial fixity. So if you are assuming it simply supported, so the WL square by 8. Otherwise, this for partial fixity, WL square by 10. W is your WU, that is your design load. So this is the design bending moment. So we have mu limiting formula, Q B D square. Q is nothing but your coefficient for mu limiting, which has been given in table IS 456 based on your concrete grade FCK and your Fy, that is your limiting values. You can also have that Q, sometimes Q is also denoted as R limiting, or sometimes it is denoted as Q limiting. So the value for M20 grade, we have using M20 grade concrete and Fe415. So for that, this 2.676 is the coefficient. This is B is 1 meter strip. D square, this is 190 raised to 2. This is nothing but, this is not 1902, it is 190 raised to 2. There is a correction here. So this is 190 square, not 1902. So which is coming around 99.63 kilonewton, which is greater than. So the limiting moment, the extreme limiting moment which is provided by this section is 99.63 kilonewton, which is greater than required, which is greater than the acting moment. So under reinforced section, the depth provided is okay. So we, whatever depth we have provided, that is sufficient. Now we need to find the area of steel. So by calculation, this approach is very much suggested to for exam purpose, because you just have this formula. If you are not getting this SP16 tables, so then you remember this. If you remember this formula, then you can easily work out the reinforcement. So mu is equals to 0.87 FIASTD minus FIAST upon FCKB. So which is, so mu we have 43 into 10 raised to 6, 43 kilonewton meter. So solving this equation, we are getting AST is equals to 676 mm square. So P is equals to 100 AST upon BD, which is coming around 0.356%, which is less than PT limiting as per under reinforced section 0.96. So we are providing 10 mm at spacing is the area of one bar of 10 mm divided by total AST required into 1000 mm, which is your design width. So the spacing calculated is 116.2. So we are providing 1110 mm center to center. So we are providing 10 mm bar at 110 center to center as per calculation. So other criteria for spacing is it should be less than 300. So it is less than 300. It should be less than 3 times the effective depth. So this is lesser in among these three values. Thus we are satisfying the serviceability requirement for cracking. So now this use of sp16 flexure table, where we by calculating this coefficient mu upon bd square. So based on this, from table number 16, table number 2, sp16 page 48, pt we are getting 0.359. So pt limiting we have for under reinforced section 0.96%. So ast is based on this, which is same reinforcement we are getting somewhere nearby. Like we are, as per calculation we were getting it's 676. Here we are getting 682. So we are providing the as per the spacing, we are providing 10 mm at 110 center. So using this was a flexure table. Now for slab table also we can check for slab design, also slab reinforcement also. This was for beam design. So slab design is nothing but a simplified beam design of singly reinforced beam. So we can also check for slabs. Also sp16 table number 23 page 64 of slab design. For a moment of 43 kN, the steel can be obtained directly for M20 Fe415, and have provided is equals to 215 mm as. So reinforcement as per this table is coming at 10 mm at 120 mm center to center, as D is 215 mm. So among these three values, we have the best design is 10 mm at 10 mm reinforcement at 110 center to center. So A stays 718 mm square 30. Use of sp16 design chart for slab and beam. So let's check one more chart. 13 page number 33 of for M20 Fe415D. Effective depth 190 mu43 के लिए percentage of steel is 0.355%. So provide 10 mm. So as per 0.355%, so 0.35% into B is 1000 into D. So D is 190. So it is coming around 10 mm bar at 110 center to center. So these tables are valid for flexure members having 50 mm to 800 mm depth. So if the thickness of the member, flexure member like beam, is beyond 800 mm, then you cannot use these tables. So in case of slab the thickness is generally ranging from 100 mm to 175 mm, 200 mm. So these tables are okay with slab design. Distribution steel, for distribution steel is minimum reinforcement 0.12% of AG. AG is gross area 0.12 B into D. D is overall depth divided by 100, because this is in percentage. So 0.12 into 1000 into 215 is your overall depth divided by 100, which is coming around 258 mm square. So we are providing 8 mm bar at this area of single 8 mm bar divided by AST required into 1000, because this is your B. So the spacing coming around 190 mm center to center. So the spacing is less than 450. The criteria for distribution steel is the spacing should be less than 450 mm and it should be less than 5 times of effective depth. So thus we have provided a safe design in cracking. Now we need to check for shear. So Vu is equals to WL by 2. This is nothing but your shear reaction. So Wu is ultimate load 17.91 into 4.9 is your effective length divided by 2. So the shear force is 43.88 kilonewton. Tau V, this is tau V. Tau V is Vu upon Bd. So Vu upon Bd is 0.23 MPa. So PT we have provided 0.35%. So from IS 456 2000, tau C we have to find tau C slab K tau V is equals to 1.18 into 0.41. This value of from using PT 0.35% and tau C we are calculating using 456 2000. So it is coming, this is coming greater than, so thus tau V is less than K tau C and tau C. Tau C is 0.415, K tau C is this, K is tau C, K tau C is this. So this tau v should be less than k tau c and tau c. So if it is more than this, then we have to design the reinforcement, we have to provide shear reinforcement, or we need to increase the thickness of the slab. So we cannot keep on increasing the thickness of the slab, we need to, then we have to provide shear reinforcement. But in our case, this value is lesser than 0.41, and it is also lesser than 1.18 times into 0.41. So hence the slab is safe in shear. So check for development length. Provide enough development length at the joint of the flat and landing, and also necessary anchorage over the support as shown in figure. The LD is equals to 47 times dia of your bar, 470. So dia of bar, main bar we have used 10 mm, so it is coming around 470, and LD by 3 is 160 mm. So check for deflections. We need to check for deflection. We have discussed the check for deflection in beam design. We have also checked this deflection check in design of slab. So as effective depth provided is more than the required for the controlling the deflection, the slab is safe in shear. So we need to just, for deflection, we need to just, that formula we have used, L upon 26. So that formula we have to recheck. So actual your effective depth is this much. So your length 4700 divided by 190, which is coming around 24.7. This should be less than your 26 MFT. We have used that formula, L upon LE upon 26. So L upon 26 MFT for continuous beam. So this 26 MFT as per as figure number 4, IS 456 2000, page number 38. For percentage of steel 0.35%, FS for FS 240 MPa. This FS formula calculation for FS is also provided in that figure, that page number. For Fe415 steel, MFT is coming 1.3. So 26 into 1.3 into 1 is greater than 24.7. That means our design is safe under deflection check. Check for cracking as a detailing requirement with regard to diameter, spacing for main and distribution steel cover for slab are satisfied as per requirement of IS 456 2000. The cracking provided is indirectly, thus slab is safe in serviceability requirement. So this means design is safe in cracking. So design is safe under cracking. Let's move to the detailing part. So this is a typical detailing of your staircase, dog-legged staircase. So this is your this is your riser, this is your thread. So this is the width of your flight, this is your first step. The wall thickness we have assumed 200 mm. This is your mid landing, which is 1 meter wide. So the total length along this direction is 4.7 as provided by problem. This height is 1.65 meter. This is your distribution steel along that direction. This is your main reinforcement, which is a 10 mm bar at 110 mm center to center. This distribution steel we have provided 8 mm bar at 190 mm center to center. This is your development length, that is 47 times your depth effective, 47 times your dia of main bar, that is L development length. So this is a typical detail of RCC staircase. So hope you have understood the design of RCC staircase, dog-legged RCC staircase design based on IS 456 2000, and we have used some clauses, some charts from SP16 for the reinforcement detailing, reinforcement designing. In case you have any doubt regarding the design of RCC staircase, you can comment. We will try to clarify all the comments. In future we'll be coming up with more videos on the staircase design. We'll be coming up with more challenging videos, but right now we are focusing on the basic design for all kind of members, structural members. So if you have any doubt, you can anytime contact us. You can comment. We will try to clarify those comments, and we will try to get back to you as soon as possible. So thank you, take care, and please subscribe to our channel and press the bell icon so that you can get continuous notification regarding our uploads. Take care. Goodbye.